Good morning. Thank you for coming to the talk. I'm quite surprised we only have very limited number of people here. This is supposed to be hot. Anyway, so my talk is really going to talk about how could we using these X-ray and proton-generated ultrasound signal for the monitoring of radiation therapy and also for the diagnostic imaging. Firstly, I will just follow up Dr. Wang's talk on the X-ACT imaging, and then I will talk about, but mostly I will focus on the diagnostic imaging instead of monitoring radiation therapy. And then I will talk about how could we using this proton-generated ultrasound to localize the black peak. So why do we interest in this kind of new imaging modalities? So before I go into any details of this X-ray imaging, I would like to, X-ACT imaging, I would like to just briefly go over those history of X-ray imaging, which could be highly relevant to my presentation. So we know 120 years ago, Rankine discovered X-ray, and for this, he won the first Nobel Prize in physics in 1901. And right after his discovery, actually has been used for radiation therapy and radiology imaging right away. But I have to point out, those radiology imaging just two-dimensional images. Not until 1972, Humsford actually found that we can take hundreds of projections of 2D images and then use computer to reconstruct a 3D imaging. And since then, X-ray CT has been widely used in clinic and just made tremendous impact in the modern medicine. And then during the long and successful history of X-ray imaging, there are some limitations has been persisted for 100 years. Number one, say in radiation therapy, you want to deliver the dose just right to the tumor, but you want to minimize the side effects to normal tissue. That's all we do as a medical physicist. And for the radiologic imaging, you really want to minimize the radiation dose without sacrificing the image quantities. So how could we do that? This is always the biggest challenge in this field. So we proposed this X-ACT imaging in 20. Oh, by the way, so the biggest concern of this image is really these X-ray images involves ionizing radiation, and all the patients just scared about those radiations. So how do we reduce radiation dose is always a big concern. And in 2013, we proposed that this X-ACT imaging could be able to visualize the radiation beam and do this radiation therapy more precisely. Like I was encouraged by Dr. Wang's presentation. Really, they did a fantastic works there, that gave us more confidence to move this technology, towards to clinic. And in 2016, we demonstrated another system which we showed that we can possibly reduce radiation dose, but still get a very high 3D volumetric imaging with a single X-ray projection. But I have to point it out, we're not the first group found X-ray compared to the ultrasound. X-ray generated ultrasound, the physics has been discovered many, many years ago, back in 1983 from a group in Cornell University in Dr. King's group. Also in early 1990s, there's a group in University of Arizona. They also found that this therapeutic X-ray can also generate ultrasound. So we just doing the imaging based on these discoveries. Like I said, I just want to more focus on the radiologic imaging side. So we want to do something similar with CT, but different. So basically, if you look at CT images, you have X-ray source, you have a detector, you want to get 3D imaging, you have to rotate both the source and detector in many, many projections, hundreds of projections to get a 3D imaging. However, it's very, very different in X-ACT imaging. You only need a single projection, just single projection. you generate this ultrasound wave. These are spherical wave. It's very different ways the propagation of X-ray goes straight as an eye, but ultrasound goes 3 dimensions. And then if you have an array, you can easily catch this 3D wave and produce a 3D volumetric imaging. So the advantage we can take with X-ray imaging versus conventional CT images, number one, we only need a single projection. We have 3D volumetric imaging. Number two, so that means we probably can reduce radiation dose. We probably can improve imaging speed because we don't do mechanical scanning. And then another advantage is really, there are some engineering advantages. You think about CT, you have to put the patient or the sample in the middle of the X-ray source and the detector. So sometimes you have limited access to the patient or to the sample. And then, but in X-ray CT, you have the source and X-ray and ultrasound detection in the same site. So it's a single site access to the patient or to the sample. Eventually, we can make a probe, portable probe, just like the ultrasound, what ultrasound was doing, is doing now in the clinic, moving around on the surface of the patient. So Dr. Wang already introduced how X-ray can produce ultrasound. I want to give you a very simple analogy, which is lightning and thunder, to more easily understand the concept. So in this particular case, you have a lightning bomb. It is an electromagnetic energy. If it's interact with the air in the atmosphere, that air will be quickly heated up and then produce a sonic bomb, right? You want to know where the lightning event is? You just count the time. Say if you count 3 seconds in multiple speed of sound in the air, which is around 1 kilometer, you know roughly the lightning event is happening in that location. And also based on the amount of sound heard, you can estimate the stress of these lightning events, right? So it's quite simple. We actually were using exactly the same concept for biomedical purposes. So in X-ACT imaging, you have this pulsed X-ray, very, very narrow pulse, not those clinic X-rays. And you irradiate this biological sample. If you have any absorber inside the tissue, this absorber will convert energy from electromagnetic into thermal, and then eventually produce a very little tiny weak ultrasound signal. That's the X-ray induced acoustic wave. And then all you have to do just to count the time and hearing this acoustic wave. First, you hear the amplitude of the signal. You get a stronger signal, you get stronger absorption. And then you hear the time arriving between you fire the X-ray and you detect ultrasound. And then you multiply the speed of sound in the tissue, and you know roughly the distance between the X-ray absorber and the ultrasound detector. That's how we do imaging. So it's very similar with lightning and thunder. We're using exact the same principles. So what are we looking at in the X-ACT images? We know in the traditional X-ray imaging, mostly we look at the attenuation. You have absorption, you have scattering of X-ray. But in this X-ACT imaging, really, we just look at the absorption. And you look at the equation there, the acoustic pressure is proportional to the dose. So we can use that to measure the dose. And then also the acoustic pressure is related with the density. So we could use that for measure, say, for example, bone density, 3D bone density map. And we, in our lab, actually, we built several generations of those X-ACT imaging systems. So the first generation is really just that back in 2012, when I was a postdoc in Nations group at Stanford, we were trying to say if we can using this X-ray generated ultrasound signal to monitoring the dose. That was the initial source. And then it's simple. We have this X-ray source, which is around 5 microseconds as excitation source, and we generate this ultrasound wave in a very low frequency range. And we just had a commercial transducer, which around 500 kilohertz, we get the signal. That's the first demonstration. And then we quantify relationship between the dose and ultrasound output. And then also we did the images. To be honest, these images are ugly, but that's like one of the first imaging we got. And then, because we know the limitation of this imaging technology is really, one of the limitations is the pulse width. So we are looking at very narrow pulse width. Rather than get 5 microseconds, how about get nanoseconds? So we get a new X-ray source which could provide 60 nanoseconds pulse, and then we can, using higher frequency transducer, we can get higher resolution. So that's the point. So, but this time we still do the mechanic scanning. It takes like tens of minutes to get 2D images, but we can improve the imaging resolution. And then, as soon as I get more money, I can build an array. And so in this ring array, we have 128 inanimate small transducers, and we build since like Dr. Wang mentioned, the signal is very weak, so we build a 2-stage of amplifiers, and we build a parallelized data acquisition system, also 128 channels, to get a 2D imaging with single X-ray projection. So that's a demonstration with, again, a high-density materials. We improve the resolution up to around 100 micrometers with a 5 megahertz center frequency transducer array. And recently, we are trying to demonstrate the concept, hey, can we, using a one projection to produce a truly 3D volumetric imaging? So we're building this cup array. We call it cup array. We have hundreds of transducers on the cup, and then we're shining X-ray pulse through a hole, and we want to make this system. We have this system. We're still working on the imaging reconstruction, trying to show you guys a volumetric imaging maybe next time. So what are the applications? Obviously, in vivo dosimetry is one, is probably the one more close to the clinic. And there's something we tried. The first one we think about is for the breast imaging. We know the gold standard in clinic is 2D mammography, which is great. But you overlap all this 3D information into a 2D images. If you look at the images on the left top, you have all this information just on 2D images. And you don't know the 3D configuration of this microclassification, which could be very important for determining the malignancy of the breast cancer. So we were trying to say, hey, can we get a 3D imaging of these microclassification in the breast? We actually get this dedicated breast imaging from Dr. Kai Yang's group from MGH, and we use it for the computer simulation. We actually get a 3D volumetric imaging reconstruction by XACT, and you can see this 3D configuration of this microclassification in this video. And also, if you quantify the resolution of this XACT imaging is around 1 micrometers. It's close to the breast CT. And more importantly, if you look at the radiation dose, it's like just 0.4 milligrade, which is a 1/10 of a typical 2D mammography. I have to admit that this is just computer simulation. We have to verify that with the experiment. And then another application is really for the bone, because X-ray has been used for the bone a long time ago. And we think we can have a 3D, instead of a clinic dual energy X-ray imaging, we want to have a 3D volumetric imaging of this bone sample. And eventually we want to say if we can look at the osteoporosis. We did a simulation again, and we also do this spectral analysis. And we actually not just do the simulation, we did the experiment. We get the first imaging from a piece of bone. And also, again, I want to mention we also we continue interested with the in vivo dosimetry. One of the work we're doing is really we have the similar thoughts. Let's move from single transducer to array, but we're making a planar array. It's a 2D matrix. Eventually, we're gonna make a 22 by 22 2D array, and we're gonna make 1,024 channels for data acquisition. That costs a lot of money. And right now in my lab, I do have a array, which is the 16 by 16 array. We're doing experiment for that. So these are the simulation for 2D dose deposition from the prostate, and also we have the 3D dose deposition in the prostate. So after I hear Dr. Wang's talk, I really I just highly encourage it. I think we really had a reason to push this technology towards to the clinic. So just quickly summarize the XACT imaging. Really, we're looking at the in vivo dosimetry. Also, we are working on the 3D bone density map. And then I'm going to quickly show that the proton acoustic. I saw many big professors sitting there, and I know you guys did another work in the proton acoustic side. And so for those people you're doing radiation therapy, know that proton therapy, you take the advantage of bragg peak, and really you want to deliver those doses just to the tumor. You want to minimize this side effect to normal tissue. So, but the question is, how do you know you actually deliver the bragg peak to the tumor, right? So you want to have a imaging technology which you can real-time visualize where the peak is. And there are many technology like out there. They could do the same thing, but we believe this proton-generated ultrasound, they can do real-time monitoring, and really you can do this range verification. So the idea is simple. You do the treatment. We're not going to change the treatment. We're not going to interference the treatment, and we just put the ultrasound transducer aside and looking at hearing this acoustic wave, and then we provide additional information on top of the original treatment. And I would say probably doing proton acoustic is more important, in my mind, is more important than the XACT, because really you want to look at the bragg peak. That's very important. And also the concept is like you have proton goes inside the tissue, disappeared, absorbed in the bragg peak. They're just not coming out. And then you generate ultrasound, it's come out. So it's like a relay. It's a concept of relay. I really like this concept. We did the simulation back in 2014. We published some papers, and recently we want to say instead of just detecting signal, can we do imaging? So we're building a 2D array to detect this proton acoustic imaging, and we're also doing the test. Since we have a very interesting machine in the proton center, we have the synchrotron cyclotron proton machine, and luckily we can change the pulse width to a very small pulse duration, so they're likely to produce a high frequency signal. So we hope we can get a very good signal from the clinic machine. And I'm working with the Dr. Yung-Chen, Dr. Ahmad, and the radiation oncology people to do the test. We spent more than a year to build the system, all the way from transducer to the amplifier to the data acquisition system. We already tested with laser, so we have laser, so we can easily test it. It's working. We are really trying to just get good data from clinic. You know that our clinic is super busy, very, very busy. They treat the patient from the morning all the way to the midnight, and we really it's hard to find a time window to acquire this data, but we're trying our best to get a good imaging from that. And so I want to quickly summarize that. Really, this is a new field, and we're still looking for the right application. But if you look at these publications, we only have very few in 5 years ago, couple of just several papers. And then over the years, last year, a single year, we have more than 20 papers published. And I know many groups are doing this, doing fantastic job. Our Michigan group, we have Colorado group, we have Indiana group, right? I saw the Professor stands there, and we have groups from UPenn. Steven is not here, but they are doing these similar things. And we have many groups out of the country. We have people from China, people from South Korea, people from Japan, people from Europe. I saw you. We're all interested with this. I hope we're gonna make this hot and really translate into clinic. So we actually write a review paper early this year with many groups from different countries on the medical physics. And also we are writing another paper with Lei because we did some work rather than biomedicine. We also translate this technology to the non-destructive testing. So with that, I would like to thank my lab members. They did all the simulations and experiments. And also, I want to thank my collaborators, mostly local people, but I do work with people across the country, also people from China. And I want to thank those funding sources. And with that, thank you for your attention. I would like to take any questions.
Okay, we have time for 1 or 2 questions.
Hi. Thank you for the talk. It's basically the same question that I had before. So, for example, in the case of breast applications, when you have a very round lesion, what would be like an approximate range of the error caused by reflection and refraction by the boundary in the estimation of the dose?
For the breast?
Or like...
Breast actually is the easiest.
Right.
Yeah, because you have relatively homogeneous.
Right.
But we do have a model to say you can, because you always have the CT, planning CT, right? You get the CT imaging first before you do the treatment. Are you talking about radiation therapy or radiologic imaging?
Like any of those, like when you're quantifying dose,
yeah,
what is the magnitude of the error caused by reflection or refraction at boundaries when you have different densities?
I don't know exact answer of the errors, but I think we have a way to solve that problem, because if you have a CT, you can do segmentation and you assign different absorption coefficient, attenuation coefficient, everything, and you do time reversal, and you can crack these errors.
Thank you.
Yeah.
A very nice talk, Shawn. I really enjoy kind of a big picture of what's going on here, and also the history. I really enjoy it. I have a question regarding your try on the bone, the osteoporosis, right?
Yeah.
So we understand X-ray has been used as a gold standard for clinic. So you are trying to do X-ray-CT. What additional information you try to get by doing that?
That's a really good question. I was thinking about this for a long time. The easiest way to answer is really, we know the signal is weak and it's easy to get signal from a bone, so we start from a bone. And then I'm thinking, hey, what are the additional information? Number one, actually I didn't show it. I want to build a device, single ultrasound array, and you're shining one pulse of X-ray. So you get 3 information. Number one is you have this attenuated X-ray hits on the transducer. And that's the same information as your X-ray, the previous X-ray absorption-based imaging. And then you generate this ultrasound wave inside the bone, so you have 3D information with a single projection. And then another information is you generate this ultrasound wave on the transducer. This ultrasound wave is propagated back into the tissue just like a traditional ultrasound imaging. So you kind of have a mechanical information. So for the bone, you have bone density, you have mechanical information, you have absorption information in 3D. So I don't know. People might be interested. So that's just, we demonstrated on the laser, but we still work on the X-ray acoustic side.